Good morning. My research paper title is Wide Band Trans-Impedance Amplifier with Bandwidth Tuning for Near Infrared Spectroscopy, Biomedical Application. My name is Muthukumaran Balasubramanian, research scholar. So here is the abstract. So WBTIA, that is Wide Band Trans-Impedance Amplifier with a tunable bandwidth for Near Infrared Spectroscopy, Biomedical Application is present in this article. So in this article, I have designed with two stages. The first stage is implemented with the modified inverter-cascode transimpedance amplifier with the series and shunt inductive peaking that is used for extending the bandwidth. And a common source, that the second stage is a common source amplifier used for boosting the gain. So bandwidth is one of the important parameter in a biomedical application. So some application we need to tune the bandwidth. So for tuning the bandwidth, so novel tuning mechanism with a fixed capacitor and tunable mass capacitor with a control voltage. So we can able to tune the amplifier with the fixed capacitor and the tunable capacitor. So for fixed capacitor provides coarse gain bandwidth tuning, whereas the tunable mass capacitor used for fine grain tuning for a bandwidth. So in my design, I have designed with the 45 nanometer technology, and the TIA gain, transimpedance gain achieved with the 84.91 dB with a bandwidth of 354.81 megahertz bandwidth. The proposed WTIA consumes 41.24 microwatts power, and the input referred noise at 100 megahertz bandwidth is 169 femtoampere per root hertz, and output noise is 69.8 picovolt per square hertz. So this is my abstract. So when you move on to the block diagram of WTIA, so it consists of 4 blocks. So first one is the TIA block, and the second is buffer amplifier. Third stage is high pass filter, and fourth stage is low pass filter. So the input current is applied to the TIA. So the TIA converts the input current into the suitable voltage, and it is given to buffer amplifier. So buffer amplifier used to isolate between the input and output, and high pass filter and low pass filter is designed for tuning the particular range of bandwidth of signal. So I'm going to explain each steps. So in WDA wideband tuning amplifier, so I have taken the existing inverter-cascode amplifier. So this is the existing basic TIA. Here, the inverter-cascode amplifier used in many optical receiver circuit, and it has a high voltage gain and reduced Miller effect, and it is a better noise performance over the bandwidth range. So in existing TIA, in this topology, we cannot able to tune the bandwidth. The bandwidth is fixed in that existing TIA. So with the help of inverter cascode TIA, I'm going to design with the tuning, control voltage tuning and fixed voltage tuning for the biomedical applications. So this circuit diagram, schematic diagram shows the proposed wideband TIA with the bandwidth tuning. So I have already told that it has 4 stages. First stage is the TIA, transimpedance amplifier, and the second stage is buffer amplifier. Third stage is the low pass filter and high pass filter circuits. So in this topology, here we have a series inductive peaking and the shunt inductive peaking is implemented. And the second stage is a common source amplifier used for improving the gain. And in the output side, we have the 4 stages of capacitor bank, stage 1, stage 2, stage 3, and stage 4. So stage 1 is designed with the 1 femtofarad capacitor, and stage 2 is 10 femtofarad. Stage 3 is 100 femtofarad, and stage 4 is 1000 femtofarad. So each one is varied with the control voltage provided with the VC underscore 1, VC underscore 10, VC underscore 100, VC underscore 1000. We can use the capacitance bank for the bandwidth tuning, and the gain is improved by the common source amplifier. So this proposed TIA, which improves the wide bandwidth tuning, and the results were obtained. So in wideband TIA, the cascode transistor MN2 and MP2 in inverter cascode TIA provides improvement of gain over the bandwidth product. And the transfer function of the inverter cascode TIA illustrated in the equation 1. And the output resistance for the MN2 and MP2 is given by the equation 2. And the inverter cascode gain is given by minus GM into Rout. And transconductance described by the equation 4. And the bandwidth is described with the equation 6. And the overall gain for the common source amplifier is minus GM N3 into RT. So in wideband tuning amplifier, I have selected the transistor sizes and the component values. So the transistor MN1, MN2, MP1, MP2, MN3, MN4, and MP3. I have chosen the W/L ratio for the better providement of bandwidth. And the components values are listed here. So in wideband tuning amplifier, the buffer is provided between the TA output and the next stage, that is a low pass filter stage. So the buffer amplifier used to provide at the output side. It isolates the two stages, whereas the output of the buffer is connected to the input of the second circuit. The buffer has the following advantages, such as low output impedance and high input impedance and the high bandwidth. So it provides a unity gain and a high bandwidth, and buffer amplifier passes all frequency without any attenuation. The next stage after the buffer amplifier is high pass filter. So high pass filter is a third stage of the TIA, which is a tunable high pass filter with a lower cutoff frequency, which allows all other frequencies, higher frequencies. So this cutoff frequency can be calculated by the equation 8. And the low pass filter is in a fourth stage of proposed TIA. Is a tunable low pass filter with a higher cutoff frequency, which also allows till the predetermined frequency. And the cutoff frequency of the low pass filter can be calculated by the equation number 9. And the band pass filter is provided, that is tunable high pass filter with a lower cutoff frequency and a tunable low pass filter with a higher cutoff frequency. So from the band pass filter, by tuning the band pass filter, the required range of frequency we can be obtained, and our proposed TIA within the range of frequency 1 kHz to 354 MHz, supported by the proposed TIA. Can able to tune from 1 kHz to 354 MHz. That will be very suitable for the biomedical application in NIRS applications. So here the design is given. High pass filter is designed for 5 kHz and the low pass filter is designed for 100 kHz. The frequency is well suited for the NIRS biomedical application. And the RNC values are chosen from the values. So resultant discussions. So the input current to the TIA, input current, photocurrent is applied to the TIA is about 50 microampere. And the output voltage from the TIA, the first stage is 880 millivolt, were obtained. The graph is shown with the input and output. That is a blue color is the IPD, that is a photocurrent of 50 microampere. And the V out is in red color, which is obtained with the 880 millivolt in the stage. So later in the amplifier, the gain is improved and the gain is obtained with a transient response. So frequency response is analyzed. So the TA gain is about 84.91 dB performed for the transient analysis from 1 kHz to 1 GHz. So the bandwidth over the range is 354.81 MHz, and the gain bandwidth product is obtained, and the phase margin about 103.44 degree. And the proposed TA has high stability, and the dominant pole is located at 100 MHz. So the frequency response of the proposed TAA is shown in figure number 7. And this one is the control voltage versus tuning capacitor. So we have increased the control voltage from 0 to 1000 millivolt, and variation with the capacitance values from 20 femtofarad to maximum 100 femtofarad. So the influence of tuning control voltage on the load capacitance illustrated figure number 8. The value of load capacitance increases as the tuning control voltage increases. When the control voltage is about 100 millivolt, the load capacitance is 35 femtofarad, and it reaches 100 femtofarad when the control voltage is 1 volt. And this figure shows the impact of tuning capacitor on bandwidth. The change in the bandwidth is inversely proportional to the load capacitor. When the load capacitor tuning capacity is 10 femtofarad, the bandwidth is 240 megahertz, and it reaches 60 megahertz when the load capacity is about 100 femtofarad. So this diagram is the impact of load capacitor bandwidth. So we have taken that 3 capacitor bank, that is 1 femtofarad, 100 femtofarad, and 1000 femtofarad. So here the achieved bandwidth for the different load capacitor is given. So for example, it is given with 1 femtofarad, 5 femtofarad, and 10 femtofarad. So the location of dominant pole is changed by the changing the capacitance value, C out, and to get the required bandwidth. The location of dominant poles for different load capacity is shown in by the 3 dots, 3 green dots. So when the bandwidth tuning is achieved by varying the C out, so the dominant location for 1 femtofarad and 5 femtofarad and 10 femtofarad are given by 60 megahertz, 11 megahertz, and 10 megahertz respectively. So this illustrates the impact of load capacitance on bandwidth. Then about the noise response. So the input referred noise given by the equation number 10. In this equation, the first term belongs to the input noise due to the feedback resistor, and the second term is referred with the MN1 and MP1 transistor. And the third stage is a contribution of MN2, and the fourth term is contribution of MP2. So these are the noise are generated within the transistor. And the last term is noise contribution due to the thermal noise and the series resistance of the inductor. So the proposed TAA, which have the input referred noise about 1.169 femtofarad, about the frequency range of 100 megahertz. This figure shows the frequency response of output voltage. So the output voltage, output noise voltage exponentially decreases as the frequency increases till 100 kilohertz. After that, it becomes constant. So the wideband TAA provides the output noise voltage of 69.8 picovolt per square hertz. So this provides the Monte Carlo simulation for the bandwidth variation. And this average about 300, standard deviation about 45, and number of passes signal is 10. And the average bandwidth is 300 megahertz, and the standard deviation is 45 megahertz from 354.81 megahertz. This diagram shows the impact of power supply on power consumption. So when the power consumption is directly proportional with the temperature, the power supply is changed from 500 millivolt to 1500 millivolt for the various temperature between minus 40 degrees Celsius to 27 degrees Celsius and 125 degrees Celsius. These are the industrial standard temperature setting. So we have analyzed the different uh, power consumption over the different temperature ratings. So our TAA, proposed TAA consume 41.24 microwatts at a 27 degree and 1 volt supply. So from the graph, it is observed that the power supply consumption is a huge when the both the temperature and supply voltage is very high, vice versa. So this is a typical layout of proposed wideband TAA, which occupies the area of 12.395 micrometer into 12.415 micrometer. So when you compare with the literature, so we have our work is proposed with the 45 nanometer technology. So obtain the gain of 84.1 dB, and the bandwidth is about 1 kilohertz to 354.81 megahertz, and the input noise current is 169 femtofarad per root hertz, and output noise voltage is 69.8 picovolt per root hertz with a 1 volt supply. The power consumed by the proposed EA is 41.24 microwatts. And tuning method, here we are going to follow the inductive peaking and mass capacitance tuning. Layout area is about 12.395 into 12.415 micrometer. So when compared with the existing TAA, our circuit outperforms with the literature number 19 and 21 with the required bandwidth range is about 1 kilohertz to 354.81 megahertz. So here the noise is very much reduced 169 femtoampere, and output noise also reduced with 69.8 picovolt. So this application, that wideband TAA, will be used for different bandwidth range in NIRS application. So in the conclusion, in the research article, wideband TAA with bandwidth tuning is proposed and implemented using 45 nanometer technology for NIRS biomedical application. The bandwidth tuning is achieved by tuning mechanism with a fixed capacitor and a tunable mass capacitor with a control voltage. The fixed capacitor provides a coarse grain tuning, and a tunable mass capacitor provides the fine grain tuning. By changing the control voltage of the tuning capacitor, the bandwidth is proposed is varied, and we are maintaining the transimpedance gain of 84.91 dB. So this maximum bandwidth is achieved 354.81 megahertz, and the consumed power with 41.24 microwatts. And the input refer noise is about 169 femtoampere per root hertz, and the output noise about 69.8 picovolt. These are the findings in our research article, and this is our conclusion. And these are the references used. Thank you.